Okay, so I did a video on intermolecular forces and really just the theory and a little bit of being able to solve a few questions, but I'm going to take a look at some past paper questions on intermolecular forces and do a few of those so you can sort of see how the examiner might test you on your knowledge and understanding of them and how you need to be able to problem solve those intermolecular forces questions. So we'll just do a few here, 5 or 10 minutes, and hopefully by the end of that you have a better understanding of the type of thing that they are after. So of course you've got a few questions here. Hopefully this comes up all right in the video. So this is a sort of standard question. We've booked it here. I'll just pick and choose a few through it. So define the term electronegativity. Okay, so electronegativity will determine whether something has a permanent dipole or not, and hopefully you all know this. And electronegativity is very simply the attraction of an atom specifically to the bonded electrons, and that's in a covalent bond. Okay, and hopefully we all remember that electronegativity increases in our periodic table from the bottom left hand corner up to the top right hand corner, with fluorine having an electronegativity value of 4.0, and that is the most electronegative element of the periodic table. We, for the purpose of this, ignore the group O and their electronegativity. So that's what we know. So the next question is, use the electronegativity values up here to illustrate the polarity of an ICl bond. So what we've got here is iodine is less electronegative than chlorine, so the electrons, we don't have to draw them on, but just to show you, the electrons will lie closer to the chlorine, meaning that it will have an uneven share of the negative charge, giving it a slightly negative charge, and the iodine would be slightly positive. And then it says use the polarity of this molecule, so we're into applying a little bit of knowledge to explain why iodine monochloride is a solid at room temperature. Well, if it has permanent dipoles, as it does have, then if I have one ICl and I have another and another, etc., we will get these attractions between the positive and negative poles. Okay, and those are your permanent dipole attractions. Okay, so we have a permanent dipole attraction here. Okay, and that requires hence energy is needed to overcome that, and therefore the question asks you explain why it's a solid at room temperature. So energy is needed to overcome that. Okay, hence it is a solid at room temperature. It's only 2 marks. We don't need to get into too many details in there. Okay, so that's sort of how we might apply it in that instance. Right, the next question then, another fairly stereotypical exam question. The melting and boiling point of the hydrogen halides increases steadily from hydrogen chloride to hydrogen iodide. Hydrogen fluoride is an exception because of hydrogen bonding, so we don't have to deal with it. Explain the melting and boiling point increase of the hydrogen halides as we go down group 7. So in other words, what they're saying there is we have HCl, HBr and HI, and this was covered in my video. And you might say, well, okay, this will be the most polar of all of these because chlorine has the highest electronegativity of all of them, and this one would be the least polar. So that would sort of bring you down to thinking, well, that should have the highest melting and boiling point because it's going to have the strongest permanent dipole, and the hydrogen iodide would have the weakest permanent dipole. But we're changing 2 variables here. We're changing the polarity of the molecule, but additionally we're also changing the van der Waals forces in the molecule, because as I said in the previous video, chlorine will only have 17 electrons in it, whereas the iodine has got 53 electrons, and obviously in between then the bromine 35. So in actual fact, despite the fact that this is least polar, okay, then the permanent dipole in between hydrogen iodide molecules is less. It's because the hydrogen iodide, the molecule, okay, has more electrons than HBr, which has again more electrons. I'm not going to write all that out. Okay, than HCl. Hence, you have greater, and I'll just write van der Waals, VDW, forces in HI than HBr than HCl. We don't need to mention anything about the difference in polarity of the bond here and the permanent dipole, because we only 2 marks. I think we've got enough there for our 2 marks. Right, let's skip on then, and we're looking this time instead of melting points and boiling points. Explain why ethanoic acid is very soluble. Now this word very is relatively important. We've got 2 marks to get, so we need to concentrate on that. So we have here an OH group, and what do we know about OH groups? Well, we know that OH groups will allow something to hydrogen bond, from the last video, hydrogen bond with water, and that leads to solubility. Now what might our second mark be? Well, if you remember in the last video, we also said that as you increase the length of the hydrocarbon chain, solubility decreases, because the hydrocarbon chain is an area of non-polar, okay, and it is what we call hydrophobic, in other words, water disliking. But the hydrocarbon chain in this molecule is very, very small. Okay, so the second mark here, you get a mark for that. The second mark will be reference to the small, and you might write 2 carbon hydrocarbon chain. And that would be the reason for the the high solubility. And the more carbons that are in this, the less soluble it becomes. And with sort of alcohols, once you go above about 4 carbons, you'll actually see 2 layers if you add it to water. So solubility decreases sharply. Right, let's look at this. The elements sulphur and carbon exist as allotropes. Okay, contrast the melting points and electrical conductivity of rhombic sulphur. So the first thing we need to know about sulphur is that it is S8, and that's just something that you'll have to recall. And graphite. Now S8 is a discrete number of atoms within the molecule, so it is simple covalent. Graphite, you should know from GCSE and AS level both, that is a giant structure. Okay, so the melting points of this is very, very low melting point. Now why is it very low? Well, it's because it's simple. Okay, simple covalent structure. We need to make reference to that. And the only forces at play here would be van der Waals. What do we know about van der Waals? They're very weak. Giant, then, when you get into giant covalent structures, okay, what type of forces are you breaking? Well, you're breaking covalent bonds, and the melting point will be very high. So as opposed to van der Waals, only in simple covalent, over here you're breaking very strong covalent, I'll just write COV, bonds. Okay, so they're very strong, and you will require lots of energy to break those. And that's the reason why any giant covalent structure has a high melting point compared to a simple covalent structure which has a low melting point. Okay, electrical conductivity within graphite, hopefully you all know that there's a free electron between the layers, whereas in sulphur all the electrons are used in bonding, so there's no free electrons, so it cannot conduct, whereas graphite can conduct because of those free electrons. Okay, let's have a look at the next one. So how many atoms are there in molecules? Well, phosphorus is P4, sulphur, as we've just done, is S8, and chlorine is Cl2. So explain the melting points of chlorine and argon. So if we look at them here, minus 101 for chlorine and minus 189 for argon. So argon has a much lower boiling point than chlorine. Now why? Well, the first thing we ask ourselves, what intermolecular forces are at play? Well, chlorine to chlorine and argon is monoatomic, so both of them will only be van der Waals. They're both non-polar molecules. Okay, so we have van der Waals, so we have temporary and instantaneous dipoles. Okay, so we have only van der Waals. That explains the very low melting point of both of these, well below 0. Secondly then, chlorine has got electrons, 34 electrons, whereas argon only has 18 electrons and therefore has got weaker van der Waals forces. So remember, van der Waals in the last video is controlled by the number of electrons. Okay, this one, I think this is one that I did in the last video as well. Anyway, explain why the melting point of silicon is so high, sulfur so low. Well, again, what type of structure do we have, and what type of bonds are we breaking is what we should ask ourselves. So silicon is in the periodic table. It sits just below carbon, and it is, like carbon, a giant covalent structure. Sulphur, as we just already established, is S8, so we're talking about weak van der Waals forces. That is a simple, and I covered this in the last question, covalent molecule. Okay, so therefore, in terms of melting it, we require very little. I'll just write capital E for energy. Silicon, okay, is giant covalent. We are breaking now very strong, proper covalent bonds between atoms, okay, and that requires lots of energy to overcome those, and that would explain the difference in melting point. You can see there it's 1410 for silicon, and it's only 113 for sulfur. And if you look at the relative positions in the periodic table, they're really very close to each other, but because this is giant and because this is simple, there's a huge difference in melting points as we go across that. Okay, so let's have a look at another couple of questions. So if we look at this one here, the forces of attraction between neighbouring S8 rings in sulphur, what are they? Covalent? No, that's within the sulphur. Each sulphur is attached, or bonded I should say, to another by a covalent bond. But if I have a ring of sulphur and I have another ring of sulphur and another one, the attraction between one ring and another, okay, has to be van der Waals. There cannot be any permanent dipole here because their electronegativities are all the same, okay, and therefore you would answer van der Waals. Explain why the boiling point of the elements increase as the group is descended. Now this is, it doesn't say here, but this is to do with group 7. So that is going from fluorine to bromine, fluorine to chlorine to bromine to iodine. And again, what happens as we go from here to here to here is that the number of electrons increases, and if the number of electrons increases, the strength of the van der Waals increases. Okay, and remember, it's only van der Waals because these are a halogen attached to another halogen, so there's no difference in electronegativity, so they're non-polar molecules because of that. Now, this is a good question here which will test us on our intermolecular forces. So boron trifluoride is a colourless fuming gas at room temperature. Melting point is low, -127, so is the boiling point. Explain why it's a gas despite having a molecular mass greater than water. So this is where shapes come into play. So water is that shape. It has a delta negative, a very significant one, and it has a very significant delta positive end. So it has an overall net permanent dipole. It has a positive end and it has a negative end, and other water molecules can be attracted to that. Fluorine is the most electronegative element in the periodic table, but we've got to take into consideration the shape, and it is trigonal planar. Okay, so understanding how shapes of molecules works is very important. We have very polar bonds here. Okay, note I said polar bonds, not a polar molecule. Okay, so the 3 polar bonds. But I cannot draw a arrow from positive to negative from one side of the molecule to the other. So if I have another BF3, okay, and it approaches this BF3, it will approach a negative area and another negative area here, and they will actually, instead of attracting each other, they will repel each other. Hence, it has a very low boiling point. So what we say here is the dipoles actually cancel each other out. So you end up not having an overall net dipole. which one of the following molecules would not form hydrogen bonds? So remember that what does form hydrogen bonds is when we have hydrogen directly attached to nitrogen or oxygen or fluorine. And note, it must be directly attached. It's not good enough to have hydrogen and one of these in the molecule. They must be directly attached. So let's have a look at the first one. Well, the answer is pretty straightforward here, actually. Okay, if we look at the first one, it doesn't have any nitrogen, oxygen or fluorine, so it has to be A. It only has chlorine, and that's not going to cut it. If we look at this one here, we have an OH group, so there'll be hydrogen bonding, O directly attached to H. Here we have an NH2 group. Okay, so we have N directly attached to H, and here we have an O attached to an H, and again OH group will give us hydrogen bonding. Last couple then. So we're going to look at this graph here and talk about the difference in boiling points. Now the first question is, consider ammonia versus phosphine, pH3. Why is the trend like this down here? But ammonia NH3 is so much higher. Well, that's because if you remember from what we did previously, just the last slide, NH3 will have hydrogen bonding, and pH3 would probably have only a permanent dipole, and hydrogen bonding are very strong. Okay, so you're looking to pick up on the fact that NH3 will exhibit hydrogen bonding and phosphine permanent dipole. Okay, the others then are back to the trend that we looked at on the first couple of questions, I think, is that, okay, these are less polar as we go up here, but you increase the number of electrons in the atoms, and that increases the van der Waals forces, therefore. Okay, so if we look at this one, if we can just see it, so the question is, which of these compounds do not form hydrogen bonds with any others in the mixture? Okay, so we've got to work out which one of these. So we've got one chlorobutane. So again, maybe we might draw this out this time if we're not quite sure. Well, that's our answer straight off, because there's nothing in there. There's no hydrogen attached to nitrogen, oxygen or fluorine. Okay guys, so that's that done. Hopefully I've done enough questions there for you to be able to answer some intermolecular forces questions. You've got the big booklet of notes there, or of questions, and you can again work your way through those yourself. And if you do have any queries or questions, you can come and see me. Okay. So if we have a look at question 14, I'll just read it out. So chloroform, which is CHCl3. So again, the important thing is that we know the shape of this, and that is a tetrahedral shape. Okay, if you don't know the shape, you're not going to be able to do this type of question. So it says chloroform has a melting point of -63. Okay, name the two types of intermolecular forces which exist between adjacent chloroform molecules. Well, the first one is going to be van der Waals, because everything has van der Waals that has electrons. Okay, and the second one then, well, can we have hydrogen bonding? No, we can't. Do we have a permanent dipole? Well, we have polarity around these regions here. Okay, so we would have an overall dipole, okay, and therefore we will have a second van der Waals, or second force, which is your permanent dipole attraction. Okay, so that's how you would work that out. The next one then, 3 accepted intermolecular forces, van der Waals, permanent dipole and hydrogen bonding, and you've got to tick which one of these have which. So again, we need to look at the structure. Ammonia is NH3, and as an A-level student you'll be simply expected to know that. So we have nitrogen and hydrogen. So yes, van der Waals, they will all have van der Waals, so we can just tick all of those. This has hydrogen bonding in it because it has nitrogen directly attached to hydrogen. Xenon is in group O, noble gas, so it's monoatomic. Therefore we will have van der Waals only. None of these others are appropriate. And then we have hydrogen chloride. So we have hydrogen, but it's not directly attached to nitrogen, oxygen, or fluorine. It is attached to highly electronegative chlorine. So we will have this distribution of charge in here. So therefore it will have permanent dipole. Okay, moving on to this question. Okay, which one of the following types of bonding can be described as intermolecular? Well, covalent, no. Ionic, no. And metallic, they're all intramolecular. They're all strong chemical bonds. So the answer is hydrogen bonding. Nice and simple. Which one of the following contains hydrogen bonds? Well, ice is water, so that is of course the answer. But we'll look at why the others don't. Iodine is I2. So that would only have van der Waals forces, induced dipoles, instantaneous dipoles. Methane is CH4, and again we would need to know the shape, but that's a tetrahedral arrangement. Okay, so CH bonds are non-polar, so that's a non-polar molecule. And quartz is giant ionic, so it's giant covalent, so that's not a simple covalent molecule. So the answer is of course iodine. Quartz, by the way, is silicon dioxide again, so okay, it won't have hydrogen bonds. There's no hydrogen even in it. Moving on to this one. Which one of the following compounds do not exhibit hydrogen bonding? Well, ammonia is NH3, so therefore it will. It's got nitrogen and hydrogen. Ethanol, CH3, CH2, OH, so we have our OH group, hydrogen bonding. Water here, of course we already know water does have it. And the final one is methane, CH4, so we have hydrogens, yes, but they're not directly attached to nitrogen, oxygen, or fluorine, so that's our answer. The electronegativity values of carbon, fluorine, nitrogen, and oxygen are given. Which of these values are most likely to be nitrogen? Well, fluorine is the most electronegative of them all. So 4 would be the fluorine. Okay. The next one is oxygen. Okay, and we'll just show you how I'm working that out. So fluorine is here, then oxygen, then nitrogen, and then carbon. So electronegativity increases in that direction. So, okay. So oxygen would be the second one, which would be there. So nitrogen must be the third one. So the answer must be B. Right, last couple then. The electronegativity of atoms causes bonds to be polar. Indicate the polarity of the following. So oxygen is much more electronegative than hydrogen, so it's delta negative, delta positive. Chlorine is just above bromine, so therefore it's delta negative, delta positive. And oxygen is the second most electronegative, and therefore leaving the nitrogen with a delta positive charge. Which one of the following molecules is non-polar? Okay, well again this is where we've got to have an appreciation of shape. So ammonia is NH3, but it's this shape, trigonal pyramidal. Okay, so therefore we have a delta negative and a delta positive end, so it's polar, so it's not that. Hydrogen fluoride, fluorine is the most electronegative of the lot, so you have definitely got a polar molecule there. And water we've already done, again because of its shape, is polar. Okay, carbon dioxide, okay, is a linear molecule. So therefore, even though that's delta positive and that's delta negative and that's delta negative, I have no net dipole where I can go positive to negative the whole way through them. So therefore the answer is carbon dioxide. Which one of the following molecules are polar? And again, shape is important. So BF3, it does, and we looked at this earlier, it does have 3 polar bonds, but it's a non-polar molecule because it has no, again, net dipole where I can draw a arrow from negative to positive or positive to negative. Okay, CF4, so if we just go down here, I'll draw my CF4, and again we need to understand that it's tetrahedral, and the same thing happens as did in the BF3 up here, in that we have polar bonds, yes, but overall our molecule, the dipoles cancel each other out, and our molecule has no positive and negative end. OF2, okay, so we have oxygen, and we have fluorine, and we have fluorine, okay, and then we have F2, Okay. Well, F2 couldn't be polar because both things have the same electronegativity. Now we just need to check the shape of this. We have two lone pairs in that, so our shape is going to be V-shaped or bent. So that is delta positive, and these this time are delta negative because fluorine is the most electronegative. So we have a positive and negative end. So our answer has to be C. And again, it's not only knowing your electronegativities and what contributes to hydrogen bonding, van der Waals only, or permanent dipoles, but it's also being able to appreciate the shape. Okay, I'll just have a look at this last couple here. So it says here, although carbon dioxide does not have a dipole, it's very soluble in water. Use intermolecular forces to explain. Well, that's because carbon dioxide, is delta positive here and delta negative there. And this interaction then gives solubility in water, where you have delta positive there. This has lone pairs, and we can get bonding between the water and the oxygen and the carbon dioxide. Right, last one then. Which one of the following liquids will be attracted to the rod? So we're really looking for a polar molecule here. That's essentially what they're asking us. So CCl4 we've already had, okay? So it will have polar bonds, but it'll be a non-polar molecule, all negative around the extremities. CHCl, so we put an H there, okay, and now we do have a polar molecule, delta positive, delta negative, delta negative, delta negative. Okay, so we have got a net positive end and a net negative end, so B would indeed be attracted to the rod. Okay, if we look at the CS2, so CS2 will be this, so the dipoles would cancel each other out if there are any at all in that, probably not. And C5H12, well, hydrocarbons, as we should all know, carbon-carbon bonds are non-polar and carbon-hydrogen bonds are non-polar, so that's a non-polar molecule, so the answer is B. Okay guys, hope that helped. Combined with the other equations, the other videos, and fingers crossed that should get you through your intermolecular forces and allow you to answer any questions which pop up in the exam.